behave as fermions. They have Fermi-Dirac statistics. In a fermion loop, you have an opposite sign. If you then add this term here, then it cancels this expression there, and you find no higher order corrections, and you find exactly this old result back. Now, these are the famous Faddeev-Popov ghost fields. And of course, what I do here is very lousy and very unsatisfactory. I have a problem. I patch it up by saying, well, I add something to the Lagrangian. And for a while we were happy with that. Then I make it a little bit more complicated, and I show to you that in tree approximation there's nothing wrong with that, and also it's exactly the same as you have in the non-abelian theories. But after a while you see that there is something which goes wrong. So I did something very terrible to my theory, with no justification. Now I find that I have to add something else, but I don't really have any other justification that I have to add something, and so I will add these ghosts. And you have to take my word for it that when I go to other diagrams, or when I go to 5-loop diagrams, these ghosts are enough to do the job. Now, in order to do that, of course, I have to give you a full derivation of this whole procedure, which requires things like path integrals and so on. But this leads to the recipe. In fact, this is the correct recipe. If you look at this a little bit more carefully, then you will see, or actually there was a plus, if I take this Fries complex conjugate away, then you see that this expression that I write here is precisely the change of the gauge condition under a gauge transformation with parameter phi. You see lambda times d mu a mu goes into delta squared xi, and a mu squared, kappa a mu squared goes into 2 kappa a mu times d mu xi. And that's not a coincidence, because that is the correct procedure. And there are proofs in the literature that if you do this, and you are willing to introduce these extra fields, which are totally unphysical, you will never have them in external lines. But they have to be there for inside the diagram to more sort of make sure that the balance of the degrees of freedom is okay. So you have to include that, and when you include it, then you can prove to all orders that this does lead you to the right results. Now, why did we never think of that some time ago? The answer is simple. If you take this kappa equal to 0, then the ghosts are still there, but they are free. There are free massless ghosts around, and whatever you calculate in terms of physical processes, since the ghosts do not really exist, they are only inside the diagram, but there will never be external ghost lines. You will never have such a diagram because it's not able to communicate with the rest. That is the situation in QED, and that's why nobody in QED discusses ghosts, unless you do sick things like I did here. But if you do the non-abelian theories, you cannot go around that, unless you choose a very funny gauge, usually a gauge which breaks Lorentz invariance. Then you can sometimes eliminate the ghosts as well. That's, for instance, one of the reasons why people use the actual gauge so in QCD calculations, because they want to make life simple. But in principle, these ghost fields are always there. It's just that in certain situations, they do not participate. They are not part of the diagrams that you have to calculate because they do not interact. Okay, I realize that this is a much more technical subject, but I thought it would be nice to, that everybody at least once in his life has heard something about ghosts and realizes that these things are there just to make sure that two theorists who do calculations, and they do it in different gauges, and they don't make mistakes, the latter is of course an assumption, they don't make mistakes, that when they bring their physics results together, they find the same answer. And for that, this is one of the technical subtleties with which these people have to cope, and on which you base, the experimentalists base their work. Okay, I think this is the end of the lectures, more or less. Are there questions?
No questions. Everybody very happy. Okay, I'd like to thank Bernard very much. Okay, last reminder, don't forget to sign up if you didn't. You will hear more about Ghost, by the way, in lectures on electroweak interactions. A little bit.
So it's not once in your life?
Twice in your life.
Ja, dus dan heb ik een dienstbeweging.
Ja, dat weet ik nog niet zeker.
So I decided to for your book.
If you give me
You give me 50 francs, he may...
And then, well, I will sketch a little what happened quite generally to the spin, what I call the spin mapping in an accelerator like that. Two cases, the magnetic field could be homogeneous, for instance, always vertical. Then in that case, if the spin, no, it's not the spin, the polarization vector would be vertical, aligned with the magnetic field, then there is in fact no precession. Because it rotates around its direction. And then there is some conservation of the polarization in that case. And then, well, if the spin would not be exactly vertical but tilted a little, then there will be a precession. According to the previous rule, the precession is gamma A times theta v, where theta v is the rotation of the velocity. And then for one turn, the total rotation for theta v is 2 pi for one turn around the ring. And then for the spin, it would be gamma A times 2 pi. And that's what we call the spin tune, 2 pi nu. And nu is just gamma A in that case, and numerically given by this formula. E over 0.440 in GeV. For electrons, and approximately the same for the proton here. The problem you see here, there is some compensation between the fact that for protons the anomaly is much larger than for electrons, but the gamma is much smaller because the mass of the protons is much larger. There is a factor 1000 approximately on both. For any direction B now, then you have to multiply all the rotations in different magnets which are placed all around the ring here. And finally, for one turn, the result is a product of rotations, and the product of rotation is still a rotation. And then if you consider the rotation for one turn, then this rotation of one turn going from some azimuth S to an azimuth S plus the circumference C is a total rotation characterized by an axis n over S and an angle of rotation 2 pi nu. That define two quantities, one n over S, which is called the spin closed solution, and the other one which is called the spin tune nu. And they have nice properties. That means that n over S is a possible trajectory of the polarization vector. It depends on energy. And for the spin tune, it does not depend on the starting point along the ring. And in general, is not equal to gamma A. It was equal to gamma A in that very simple case, but that's not very general. Well, the time is running on, so maybe I will try to skip a few things. According to this properties of rotation, you can manipulate your spin, in fact, and then it's usually done designing spin rotators, for instance, and then you can manage different bandings, horizontal and vertical, such that the spin at some place here would be longitudinal and restored vertical after that. And in fact, spin motion, you can say that it's a new degree of freedom, because in fact, effectively, you can use it, you can manage with it what you want. Spin orbit coupling now. Now, up to now, I've considered only one particle, I would say. And I followed the motion of one particle. Let's now consider a beam of n particles, and then the things becomes much more complicated because each particle has one trajectory, and the trajectories can differ from one particle to another particle in the beam. And for a given trajectory, you have a given field which depends on this trajectory because it depends on the transverse position x and z along the ring, and the azimuth s along the ring. X and z are the transverse coordinate of the particles relative to some reference. But you know that this field then fixes and gives the precession vector of the spin, of the polarization, in fact, and then determines the spin motion, the polarization motion. Then you have a coupling trajectory giving you a spatial given motion. And different trajectories will give different spin motions, in fact. And then if different particles have different spin motions, then immediately you can realize that the directions of their spin could open in some way, and then the barycenter of the different polarization vector of the particles will go down to 0. Then you have a depolarization. And then that's illustrated in the case of a vertical trajectory of the Betatron type here. Then in a magnet, the field is not exactly vertical, transverse to the velocity, and in the quad, you have a field which is proportional to the displacement. And especially due to that one, in the quads, the spin will not stay exactly vertical because it will rotate around this horizontal field here. Well, I have a problem because if I want to show you the movie, then I will be a little late. Why not project the movie tomorrow? Okay? That's because I am, in fact, entering in the most important point here. Well, you have the use that in physics, when you have a quantity which couples to another one, then there is a reverse coupling. The second quantity acts also on the first one. So you can ask about the reverse coupling, would mean the spin motion would influence the trajectory of the spin of the particles. So you would have a spin-dependent trajectory. And you have learned that at the university. There is a famous Stern and Gerlach experiment to separate spin states. You introduce atoms in a very inhomogeneous field here, and then you discover that your beam of atoms is split. For if the atoms have spin 1/2, they are spin in 2, one will spin up and the other one will spin down. So that's well known. What happens in our case? You can effectively look at this reverse coupling here. Going back to the Hamiltonian, the scalar product of omega BMT times the polarization vector S here, developing that, considering that essentially you have consider the most important case of a transverse field, B perp. The force on the trajectory of the particle is given by the gradient of the Hamiltonian with the minus sign, and then you get that. So in the Stern-Gerlach experiment, the rotation of the trajectory here, dp over ds, here, Stern and Gerlach, is given by the first time dt over ds, and then you get this formula, E over 2a lambda bar c, where lambda bar c is the quantum wavelength of the particle h bar over mc. And let's recall that for the velocity, you have a similar equation according to the Lorentz force, ECB, and then you get EB for dp over ds. And then you can compare both, and then say, for instance, that the gradient of B perpendicular is essentially given by some formula like 1 over B dB over dx here. And then the ratio of both here, especially if beta is 1 at high energy in the relativistic region, then the ratio is given by this product F lambda bar C. But A lambda bar C is very, very small, and A is usually also not larger than 1. And then you get these values for A lambda bar C. and then you see it's 10 to the minus 14 centimeter. So it's a very, very, very small number. So it's effectively completely negligible at high energy. It's only if beta would be very, very small, like in usual Stern and Gerlach experiment, that you can see important effect. So you can forget, in fact, the reverse coupling. How now you can have depolarization? Essentially, this depolarization is resonant, as you will see. Let's consider the first case, the simplest one, where there will be no depolarization. Perfect. Everything is perfect. Your ring is perfect. What does that mean that you have an ideal ring? That it is in a completely plane, horizontal, for instance, and then in that plane you have a proton beam, for instance, no radiation, so it's a proton beam circulating and completely flat. All the motions of the particles are only in the horizontal plane. And your spin is vertical, your polarization vector, so it's strictly vertical and precess on the B. Yeah, in fact, there is no precession because it's strictly parallel to B. And then you have no depolarization. That's perfect. And you are happy. So, and then you would say, well, there are betatron and synchrotron oscillation, but these oscillations are in the horizontal plane. And then the different particles will see maybe different vertical fields, because they are entering in quadrupoles, for instance, where they will see also a vertical field due to this excursion of the particles transversely. And I would say that this is a spin-transparent lattice. That means nothing happened to the spin. It's conserved. Sorry, not the spin, the polarization vector. Well, starting from that, I will complicate the game a little because the reality is somewhat different. But, well, to be very simple, I introduce a small perturbation first. Only one. Your ring is still completely perfect, but I have this small perturbation here, a small solenoid that I've introduced here, creating a longitudinal field, which will be an RF field, because you here have some AC generator here. So I have this perturbation here. The integral of this longitudinal field I call BL, behaving like cosine of omega t with a frequency omega, which is fixed by your generator. Then I represent it mathematically like that because this field acts on the particle on each turn. So I introduce the delta function, or a series of delta function, to represent the kick given to the spin, the polarization vector, turn by turn, S minus NC. N is an integer here. At each turn, N increased by 1. And this cosine here is just this cosine omega t. I have replaced the independent variable t by S here, and I'm obliged to introduce omega 0, the revolution frequency, and the mean radius of the ring. Then, as usual, I perform a Fourier analysis of that, and then Fourier analyzing that, I get BL over 2C, sigma over n, and sigma over the plus or minus sign, e to the n plus or minus q times theta. Theta is the usual S over R variable, independent, and q is the ratio of the frequency of the RF field compared to the revolution frequency here. And then if I pick up only one component of this Fourier spectrum here, the component with the frequency n plus or minus q here, times in amplitude I call Bn, which is essentially BL over 2C here, then this number, this complex number here, represents a vector rotating in the horizontal plane here, and rotating with this frequency n plus or minus q omega 0. So in fact, my solenoid here has introduced a rotating vector. And this rotating vector will act on the spin. If I look at that in the laboratory frame, here you have the polarization vector tilted maybe from OZ here, and you have this perturbing rotating field Bn rotating around the vertical in the horizontal plane, like that. And then I can represent that also in a rotating frame. I attach to this field a rotating frame, rotating at the same frequency then, such that this perturbing field, Bn, will be fixed in that frame here, fixed along the capital X axis here. And then in this rotating frame, the motion of the polarization vector will be described by two rotation vectors, one around the vertical, the previous one given by this vertical magnetic field here, and another one along OX here given by this perturbing field. And then they are given by this formula in units of the cyclotron frequency. Omega n over omega c is 1 plus a bn over b. The 1 plus a here comes from the BMT equation and from the fact that this perturbing field is longitudinal and not transverse in that example here. And omega, this capital precession around z here, is the previous one in the laboratory frame given by the spin tune nu, but as the frame is rotating at this n plus or minus q frequency, I have to subtract that. And then you see that the result of these two rotation here is a resulting rotation vector here, which is tilted from the vertical, and the spin does not precess no more around the vertical, but about a tilted axis. And that will give you a resonance when this omega vector here goes to 0, because then omega r will be along the x-axis. Let me look at that in more detail. There are 3 points in that transparency. I describe first what we call a spin resonance. What is the resonance crossing? What happens when you cross the resonance? And why you have depolarization. Because I want to be maybe a little slow because I will finish. I would prefer to be maybe slow. In fact, we'll be obliged to skip many things. But it's essential to understand the basis. So first you have a spin resonance, and that's 3 pictures here describe what happens in different situations. Nu above nu r here, then omega r, the resulting rotation vector is a little tilted from the vertical, and s rotates about it. The other case, nu smaller than nu r, then omega r has flip on the other direction here, so it's still tilted from the vertical, and S again rotates around this tilted axis. These 2 situations are a little symmetric. And between them, we have an intermediate situation here when omega, the rotation about the vertical, is 0, vanishing completely, and then you are left with an omega r equal to omega n here, which is along the x-axis. And then your spin rotates now around the radial axis x here and makes and describe a large circle like that. It means that the vertical component of the spin as z goes periodically from minus h bar over 2 to plus h bar over 2. And then that's what we call a spin resonance. And it has, we can define a width of the resonance when the tilt of omega r is exactly pi over 4. And that's, it means when omega is equal to omega n plus or minus. And that's the width is usually, in that case, given by epsilon equal 1 plus abn over b. Now, second step, what happens when you cross the resonance? Now, that means that you increase the frequency of your perturbing field. You adjust this frequency, or you change it. So nu r, for instance, is increasing. You do not change the energy of your particles, and then at some point, nu r becomes equal to nu, and after that, it becomes larger than nu. That means that you have a frequency modulation of your RF field. You can do that in 3 ways. Either you go very fast to change the frequency of your RF field, or you do it very slowly. On an intermediate case, you do it in a moderate way. So you define a variation by unit time, dq over dt or dq over d theta. I take theta, the azimuth s over r, as the independent variable, and this gives me the derivative of the frequency gamma here. And gamma, if I am very fast, could be much larger than 1. It means that in that case, for instance, you cross the resonance in less than 1 turn. Nothing can happen to the spin in 1 turn, and it's too fast. Then immediately the result is that the final polarization is identical to the initial polarization, especially its vertical component. In the opposite case, you do it very slowly. In case, then your spin precesses around omega r much faster than the change of the direction of omega r. So you have an adiabatic change. And then in that case, the spin follows, in fact, the vector omega r. It is attached to omega r because it presses around it very fast. And then omega r rotates because it will start from OZ, becomes horizontal, and after that going down, downward. Then immediately the polarization vector will do the same thing, start vertically, and finally becomes aligned in the opposite direction. SZ is equal, final is equal to minus SZ initial. And then we have an intermediate case where gamma is of the order of 1. And then you have to look at some literature on that, and there is a formula, give you a formula, because then very likely the final value will be intermediate between +1 and -1, and then you get something like that. It means that your spin will not be finally vertical upward or downward, it will have some direction. And the question is, why do you have depolarization? I've made some rotation of my polarization vector. Well, but why it would be depolarized? But that happened after the crossing, essentially. Because if you now look in this moderate case, what will happen? For different particles, you will have their polarization vector S1, S2, S3. In the case, for instance, of only 3 particles, it will not be exactly vertical. And then they will precess around the vertical direction. But now, you remember that in a beam, usually the particles have not all the same energy. You have some dispersion energy. And you remember that at different energies, particles will have different spin tune, then they will precess at different frequencies, in fact. Delta nu over nu would be equal to delta E over E because they are proportional, nu and E. And then immediately the phases of the different polarization vectors of the different particles will mix. And then effectively the barycenter of this vector here will go to 0, will decrease. And in fact, does it decrease to 0? That's not sure. If you do a simple calculation of that, there is a formula giving that. And nu over QS delta E over E. Delta E over E maybe of 10 to the minus 3, QS maybe 10 to the minus 4, nu maybe 1, for instance, at low energy. So that's a small number. If you go to high energy, it's not obvious. Okay. Maybe it will be the good time. Just one point. 1 minute more. We'll stop there. No, but the video will stop. 2 minutes. Okay, fine. Just to present this transparency in order to stop at a good point. Obviously, this situation is very similar to what we have in nuclear magnetic resonance. Because in nuclear magnetic resonance experiment, you have also an RF field exciting some nuclei with spin here. Then we have done, and you have a stationary field also. And so you have precession of the spins of the nuclei or the atoms in this main field, plus a perturbation given by this RF field. Exactly the situation I have just described. Nothing really different in principle. The reality is different because effectively it's not the same experiment. And then you have a spin resonance at some frequency. And because your RF field could be also described by two rotating vectors, one in one direction, one another in another direction, B plus or B minus. And then you have a resonance with B plus, for instance, when the precession of B plus is equal to the precession of the spin about the main field here. And then that means that the spin will precess on top of the resonance between the two states, and you have absorption of RF energy. And just to finish, goes to be very general now, abandon a simple perturbation here. Now, maybe my 2 minutes are finished, no? Well, okay, I will stop here because it takes some time. Okay, I will stop here, I think.
Very detailed lecture. Any questions, Suzanne?
Interaction gives you exactly the diagram. You can see that because you see if you make this line with the phi's, you call this momentum P and the other one Q, then there is a certain orientation in the diagram. If this is phi complex conjugate and this is phi, and this is phi complex conjugate and this is phi. And on one of, when you have the phi term, then there is a d mu term here. So in this case here you find q mu, say, and in this case here you find p mu. And of course there is momentum conservation, and the propagator, the interaction is proportional to 2 times kappa, and the propagator, since there is this lambda term here, has a 1 over lambda, so I get kappa squared over, for each of the propagators, 1 over lambdas. So I get, roughly speaking, depends on how familiar you are with Feynman diagrams, this gives me exactly the same result as that. That doesn't show anything at this point because I'm only looking at those terms which are not